Okay, so I mean the first part. So this is 2017. Question 4. Although we can make quadratic residues. So in these setups, we always have P being an odd prime, i.e. it's a prime strictly greater than 2, so it's not the prime 2. And the setting is we're working in ZP, the multiplicative group of congruent classes modulo P. And so first thing to be very clear on is what's the definition of this term quadratic residue. So the quadratic residues are the squares. So an element n from ZP is a quadratic residue. So this the definition of this term is a quadratic residue if there exists an element such that n squared is congruent to n modulo P. Or if you're working within the group, you might just say n squared equals n. And so n is the residue that's left behind after dividing a square by P. That's the total residue. It's a quadratic non-residue if there does not exist such an n. If the m exists, it's a residue. If the m doesn't exist, it's a non-residue. I'll just send around to just sign in on that sheet there. Okay. So for part B, you're asked to prove that exactly half of the elements are quadratic residues. So ZP has P minus 1 elements, half of which namely P minus 1 over 2 are residues, and half are not. And I mean, the key idea in terms of, how to learn these proofs as such, why is it half? The key idea is that when you square something, you're going to get a residue. But when you square its negative, you also get the same thing. Okay, so there's this doubling up effect that happens. Okay. When you square a negative, you square minus a, you always get the same. You always get the same as a. Okay. And in general, that's always the case of a and minus a are two different elements of ZP. When a is in ZP. But just pause there, because sometimes when you're working modulo or modulus, a number is its own negative. If you're working modulo 10, 5 is congruent to minus 5. But that's only the case for even numbers, where exactly half that number is congruent, or exactly half the modulus is congruent to its own negative. But in the case of odd primes, that can't happen because they're odd. So an element A is always distinct from its negative, but when you're squaring, these two always go to the same thing. So of all the elements that you have in ZP, all the elements that you have, when you square them and go this way, to get a bunch of elements down here, which are going to be the residues, because they arise from squaring. There's this doubling up that happens. Okay, so two elements always do the same element, because this is A and minus A, this is B and minus B. So that's kind of the key idea. Now, what's still, so that kind of persuades us why it is this kind of half the elements, because you get this double it up. So it can't be more than half. So if we're always doubling up when we move from the top to the bottom, but at most the number of elements at the bottom is half the number at the top. What could still happen, what isn't immediately obvious, doesn't leap off the page necessarily, is maybe when I squared B and minus B, maybe they also went to the same thing as the square of A. Maybe B squared would be congruent to A squared. Okay. So that's something that we have to prove can't happen. Yeah, because if that started to happening, then you'd get more than doubling up. You'd sometimes get 4 elements up here that went to the same element, 4 or more. So that means there would be less than half total number of residues. So this is the key idea, that when you square something and it's negative, you get the same element. So we just want to present that formally. Well, yeah. So first, notice in ZP, an element A is always distinct from its inverse, from its negative. And so when you start squaring things, you only need to go up to the square of p minus 1 over 2. We don't need to square any of the other ones because the numbers after p minus 1 over 2 are just the negatives of all of these. P plus 1 over 2, the next integer, is the negative of p minus 1 over 2. Until you get all the way to p minus 1, and the last element in that, so to speak, but p minus 1 is the negative of 1. So these numbers are all the residues in ZP, since the other number is p plus 1 over 2, p plus 3 over 2, all the way up as far as p minus 1 are just the negatives of these. Of course, a squared is always common to minus a squared. So that's trying to write down precisely just this insight. Okay? That these numbers here are all of the residues. If you're looking for a residue, you will find it on this list. What we haven't ruled out yet is maybe 2 of these elements on this list are the same numbers. So that's the remaining part. So at this point, we know that there's at most p minus 1 over 2 residues. Okay? Moreover, all the elements in the list above that list there, all these elements are distinct. But we should give a little proof of that. Yeah. Or suppose that we have two congruence classes, two elements x and y inside this range, p minus 1 over 2. Suppose we had two of those and we had that x squared was congruent to y squared mod p. So I'm supposing that I took two of the elements from the first half of elements and that their squares were congruent to one another. Well, that would imply, by the definition of congruence, that p divides x squared minus y squared. And it should just happen in front of our eyes. Anytime we're looking at a difference of squares, we should immediately think of that as the product of the sum of the difference. So that's, of course, the product x minus y over x plus y times x plus y. And we're basically going to prove that p must divide this factor. P must divide this factor. That means x is congruent to y. So in effect, I've just taken the same element twice. That will prove that they are all distinct. But how do we get to that? Well, classic case now, you've got a prime p dividing a product of numbers. So that immediately tells you, thanks to Euclid's lemma, that if a prime divides a product, it must divide one of the factors. That's an equivalent definition of what a prime number is. It's a number that has the property that whenever it divides a product, it can only do so by dividing at least one of the factors in the product. Composite numbers can achieve division of a product a different way by having some of their factors and some of the factors over here. So the composite number can be split up in a little bit of it in the first factor, a little bit of it in the next factor, a little bit of it in the next factor. Prime numbers can't be split up. So the only way they can divide a product is if they divide one of the factors. Okay. So that implies that p divides x minus y, or p divides x plus y. You might divide them both, maybe. That's by Euclid's lemma. Or we might have called it a theorem. Now what we want is this. We want that p divides x minus y. That will show that x is congruent to y, which I want to do. So we just have to rule out the fact that p could divide x plus y. Consider x plus y. You see, well, how small can x plus y be? The smallest x plus y can be is 2. Because x and y are both bigger than or equal to 1. And the largest x plus y can be is p minus 1. Okay? Because they're both less than or equal to p minus 1 over 2. And we're considering, could this happen? Could this happen that p divides the sum? Could p divide a number in this range? Well, no, because there's no multiples of p there. There's an early multiple of p, which is 0. 0 is a multiple of p. Then the next multiple of p you get in the integers happens at p. But we don't go that far. We stop at p minus 1. But there's absolutely no multiples of p in that range. So you can say that p does not divide x plus 1. So therefore, p must divide x minus y. It either divides x minus y or it divides the sum. We've ruled out the fact that it can divide the sum, so it must divide the difference, i.e. x is congruent to y mod p. So what that is there a proof of that claim at the top that all the elements in the earlier list were distinct. And this proves it because if you take two elements in the earlier list, suppose that they're the same, mod p, after you square them, then the conclusion you're forced to is that, well, in fact, you must have just stupidly taken the same element twice. And so if you take the same thing, of course, when you square it, it's going to be. So, therefore, include all the elements in the list star are distinct. And this proves something. Okay. Yes.
Just why do you say that it doesn't divide x plus 1?
So, like, you think of the numbers like it's because we've. Are you okay with reaching this line in deciding that x plus y is not between these two? So, well, it's simply because there's no multiples of p there. So, like, say p was equal to 7, right? So we're saying that the sum is trapped between 2 and 6. Can 7 divide a number between 2 and 6? No, because there's no multiples of 7 there. Yeah, all these numbers, they're bigger than 0. 0 is a multiple of 7, but they're smaller than 7, and there's no multiples of 7 between 0 and 7. Yeah. So we've trapped x plus y in a range of integers where we can say that there are no multiples of p. So x plus y cannot do that. Any other queries on that? Or no? It's okay. So the key idea to remember is this doubling up, which naturally happens when you square. So the doubling up on its own is enough to prove that there's at most p minus 1 over 2 residues. And then you need this extra proof here to show that there's exactly p minus 1 over 2 residues. So we always get a pair of elements from ZP, A and it's negative. Square them, they go to a certain residue, A squared. But when you take a different pair, a different element B, and it's negative, it isn't going to go to A squared as well. It's always going to go to a new distinct element, B squared. So you're exactly halving the number of elements in ZP. Yeah. Question? Brief in 2016. Okay.
It's just that it's like 2 parts to it, those 10 marks, and I don't really know where you get all of them.
Okay. Okay. So, 2016, I think I have to bring up the computer.
I've got one if you want.
Have you got one there? Yeah, do I take that? Okay, so these are, okay, so these two. Well, the second part is proving that there's an infinite number of prime numbers, equal to proof. And the first one is, yeah, proving that there are arbitrarily large gaps between consecutive primes. That's what we have to prove. So that means, so we're talking about in the sequence of integers, 1, 2, 3, 4, 5, 6, that so there are arbitrarily large gaps. So if someone asks you, show me a gap of 1 million, you should be able to point to a place in the sequence of integers. Okay, at this point here, here's a prime number here, and for at least the 1 million integers after it, none of them are prime. So the next prime, so that's what we mean by consecutive primes. There's a certain prime here, and the next prime after it comes at least after a gap of 1 million. Okay, maybe some more. That's what we're being asked to prove. And so this was a companion result to the twin prime conjecture, hasn't been proved yet, which says that there is an infinite number of primes as close as possible to each other. Close as possible to each other are primes like 11 and 13, primes that are 2 apart. Okay? Those are called twin primes. There's a conjecture that there's an infinite number of those. It hasn't been proved yet. They've recently, in the last few years, they've been able to prove, kind of approach it. They've been able to prove that infinitely often neighboring primes are at most fixed distance apart, but that fixed distance is still quite large. It's still in the order of thousands. Thousands maybe. Okay, so that's what I like about it is the twin prime conjecture is obviously hard and has produced a lot of good mathematics and people working towards it. And this is almost, when you first read them, this result almost seems like a result at the same level, but it's a second example. Easy to do. Okay. Now there's a bit of a hint or a reminder. So first of all, it spells out exactly what this phrase arbitrarily large gaps means. So prove that for every positive integer m, so m is the size of the gap, and there exists a pair of consecutive primes, p1 and p2, satisfying that, well, the distance between p1 and p2 is at least m, strictly variable. And so that's just spelling out exactly what the result here is. And here's the hint is that make use of the factorial to do this. And carefully state any properties of divisibility that you rely on. Okay, so let's put this down. Yeah, so there isn't much splitting up of the 10 marks, but you know, it's you want to produce the correct argument and just take account of this instruction to carefully state any properties of divisibility that we rely on. So we'll try and do justice to that instruction there. Okay, so this is the way it works. Consider an integer n that we have. Once we make this, well, let's just make it bigger than. So just a positive integer. And we'll consider the factorial. Now, which factorial are we going to take? You see, it's going to start with 2. And consider the factorial, n factorial. So this is n times n minus 1, n minus 2, all the way down to 3, 2, 1. Okay. So first of all, we'll get the insight about the divisibility. Right. So we say, notice that 2 divides factorial. Wait a minute. Sorry. Consider the factorial, n factorial, and the sequence of integers. So again, here's the sequence that's going to be constant. N factorial plus 2, n factorial plus 3, n factorial plus 4. Okay, that's clearly a sequence of consecutive integers. I'm starting at a particular point, n factorial plus 2, I'm adding 3, or I'm just adding 1 to get to the next one. And how far can we go? We can go all the way to n factorial plus n. Yeah. Now the claim is each of these is composite. Each of these are composite. As little j always divides n factorial plus j for every j between 2 and n. Since, well, n factorial plus j certainly, since j divides n factorial, and n factorial plus j, here's the bit where we're just defining the properties of stability is a linear combination. A linear combination of numbers divisible by j. And hence is divisible by j. Okay, that's kind of a wordy description of it, but you know, as long as you do something equivalent to that. You make this observation that the integer j always divides n factorial plus j, and that's true for every j between 2 and n. Okay, since j divides n factorial part, j obviously divides itself, and so n factorial plus j, just the sum of them, that's a linear combination of two numbers that are divisible by. That's that key early on property of divisibility. A number divides two terms, it always divides every linear combination of two terms.
Why did you start off with n factorial plus 2 instead of?
Well, so if you start, so the way the proof is going to finish is because these elements are all composite. You know, there'll be some prime before them and there'll be some prime after them, and the gap between them will be at least whatever that gap is. Well, why didn't I start at n factorial plus 1? So what would the claim be about n factorial plus 1? That it's divisible by 1. But we knew that anyway, and that doesn't help us say whether or not it's a prime. Indeed, can a factorial plus 1 be prime? Well, I mean, I can't think of an obvious reason why it can't be prime. It is an odd number, even number plus 1. It could well be, you know, I can't think of a reason at the moment. Anything else? Why factorial plus 1 might not be prime? I mean, it probably isn't for any particular n, because most numbers aren't prime. But so that's what we started thinking. So we want to get a non-trivial factor. Yeah. And we can only go up as far as n factorial plus n, because what about n factorial plus n plus 1? I mean, it's not that it's not composite. It certainly isn't compelled to be a prime, but it's possibly a prime. N factorial plus n plus 1. Well, there's no immediately obvious reason why it must be composite. Still probably is composite. All numbers are probably more likely than not composite. But you know, we can't say. So so these numbers are all composite. So this is a run of how many numbers are here? Well, there's capital N minus 1. N minus 1 consecutive composite number. So if P is the largest prime less than n factorial plus 2, the last prime before you get to n factorial plus 2, q smallest prime bigger than n factorial plus n, then the gap between p minus q, well, if this gap is n minus 1, then the gap between p must be at least n. Okay, and there's nothing, we can choose n as big as we want. We can make that gap between those two consecutive primes as large as possible. So the gap between p and q can be made arbitrarily large. Large as we want. Euclid's proof, shall I do Euclid's proof again? Doesn't it? Yeah. Good. So, any other? Types of question? And I'd also encourage you to make use of, all the tutorial questions in the notes as well. Just focus on the past questions. Any particular types of question or chapter or anything? Anything like to come? I mean, one thing that we did very early on was the induction proofs. And some of them were not so straightforward, perhaps. Can you remember these? These ones, and then I believe there was a few in the divisibility chapter as well. Yeah, so in the first chapter we had various, these are often kind of initial examples of induction. You see various summation formulae or quantities perhaps. And then in the divisibility chapter we had various divisibility results. We should do 4C there. That seems to be a tricky, well, let's go with this minus 1 to the n plus 1 factors, so plus or minus sign. Oh, yeah. We're using induction to prove here that 3 always divides 2 to the n plus minus 1 to the n plus 1. For every n bigger than equals 1. So this expression here, 2 to the n plus this power of minus 1, that's either 2 to the n plus 1 or 2 to the n minus 1, depending on whether n is odd or even. So the result is saying that either 1 bigger or 1 less than a power of 2 is always going to be a multiple of 2. And induction is so important because induction is really the thing that is the quintessential property of the integers. Okay? We know all about properties of integers, how they add and multiply, and all these kind of algebraic type properties. But they are kind of equally true from a kind of axiomatic viewpoint. They're equally true the rational numbers, the real numbers, complex numbers, and so on. But it's this principle of induction, the fact that you can prove things about all integers using induction, is what really separates the integers away from the rationals. So in a number of key points in the course, when you look back at the proofs of the various properties that we've masked there, induction, or using the principle of induction, often in that. So this kind of thing is like a workout or a training exercise. So induction cases always begin by, well, this simple kind of induction by examining the base case. So the base case, n equals 1, is the claim that 3 divides 2, and if n is 1, so this is minus 1 squared, so 3 divides 2 plus 1, which is clearly true. 3 divides 3. So then we say, then what do we say? Then, so that's the base case, that's where we start. Then the next thing we do is we assume it's true for some result in this domain. And we assume that 3 divides 2 to the k plus minus 1 to the k plus 1 for some integer k greater than equals 1. And we're allowed to make that assumption, or it's not an obviously wrong assumption, because we've just proved that it does happen at least once. So, you know, it's not like we're going to go obviously wrong by pretending that this result is true, because at least we know it's true once. Because if you started off by, imagine we didn't do the base case first. If we started off by proving this, someone could immediately object and say, "Oh, well, you're making an assumption there. How do you know it ever happens?" Or, you know, so that might be, you know, something that might stop us in our tracks. The argument. Okay. So you've seen that this, and so now we will try and deduce. That's the try. We will reduce from this the result for k plus 1. Okay, so here's the number for in the k plus 1 case. Where is it?
You need to spread that blind along.
Okay.
No.
No. I think we're the very last thing.
Very last thing you do.
Okay.
It's always the last place you look.
Okay.
Sorry.
So my first instinct would be to take this and see what that divisibility assumption says is that 2 to the k plus minus 1 to the k plus 1 equals 3 times q for some integer q. Okay, Q is the quotient of this thing divided by 3. So I got to somehow build this quantity out of that quantity. So my first thing would be to divide it by 2. Okay, so I'm going to say, so this line hasn't finished yet. It's not a full stop. But what I'm attempting to do is attempting to show that this thing is 2 times the expression from the start. And we do get 2 times 2 to the k, which gives us 2 to the k plus 1. Good. But then I get 2 times this, which gives me plus or minus 2. It's not what I wanted. I wanted plus or minus 1. But now you notice that the exponent on the minus 1 here is 1 different. So whenever this quantity is minus 1, this quantity is plus 1, and vice versa. Whenever this quantity is plus 1, this quantity is minus 1. Their exponents are 1 off. So that means whenever 2 times this, whenever 2 times that is plus 2, what I really want is a minus 1, and the difference is 3. It's good. I'm going for divisibility by 3. And whenever this 2 times this gives me a minus 2, this is actually a plus 1. So again, the difference is 3. So what we're saying is we have to add on 3. Well, we either have to add on 3 or take it away. And it's just going to be some power of minus 1. Well, when this thing is a plus 1, so when k plus 1 is even, that's a minus 1, so I end up having to take away 3. But when k plus 1 is even, this has got to be negative 1, so I can just make that k. So the only tricky thing to get is, tricky thing there is just marshalling the exponents and getting them right. Okay? Equally well, you could have made it k plus 2 or something, just something that has the same parity as k. Now, what I'm trying to achieve is to show that this thing is divisible by 3. Near that yet, because I've got it written as 2 times something which I know is divisible by 3, and then maybe another 3 or 1 less 3. So the whole thing will be divisible by 3. So this is 3 times 2q plus or minus 3. Hence 3 does divide 2 to the k plus 1 plus minus 1 to the k. So that's the induction step. We assumed it was true for n equals k, and using that, we were able to reach the conclusion that the result is also true for n equals k plus 1. So by the principle of induction, we can say 3 divides this thing for all n. We've shown the base case, and we've shown the linking step that each case implies the truth of the next one. Base case is true, so that n equals 2 is true, n equals 3 is true, n equals 4 is true, n equals 5 is true, and that process is going to count us through all the integers. And maybe a more so that way there of messing around with the exponents, maybe a better. Sometimes I don't do those in the best way, or I tend to tie yourself up in knots. I think you can do it in a more direct way. When you get from this point here, where you know 2 to the k plus minus 1 to the k plus 1 is 3 times q. I I'm just trying to think of easier ways to do it. You can then write 2 to the k is 3q minus 1 to the k plus 1. Now minus 1, you've got an extra minus sign there, so you can bump that up to minus 1 to the k plus 2. And then that would imply then, if you just want to generate the next power of 2 to the k plus 1, well, there's obviously 2 times that. And that would give us 6q plus 2 times minus 1 to the k plus 2. Yeah, and then just add an extra minus 1 to the k plus 2 to both sides. 2 to the k plus 1 plus minus 1 to the k plus 2, 6q plus, so I'm adding this to the left-hand side, so I better add it to the right-hand side. And you've already got 2 of them, so now I've got 3 of them. And this thing is divisible by 3. 2q plus that. Maybe a more, just maybe, yeah. Maybe an easier way just to tell you how to handle the exponents. You see here the exponent just turned out to be k plus 2 on the minus 1. My original treatment, I put it as k, but of course they're going to have the same value. Minus 1 to the k, minus 1 to the k plus 2. Be the same value. Okay, good. Let's finish there for now. So have you seen? No, it's not me. It's John who's got the lecture tomorrow evening, but I'll be doing the 2 tutorials on Friday. So we'll do some more revision activities then as well.